talking about volcanic fissure and associated deposits on the North Massif of the theTaurus-Littrow Valley, source of the Apollo 17 very low titanium basalts.
Thank you. Notice the question mark at the end of that because, as you'll see, the story has evolved substantially since we started presenting this at LPSC this past year. I want to take a moment to thank the co-authors, and actually Barbara Cohen should be listed on there as well because she's provided some valuable discussion as we attempt to unravel sort of a new mystery about the theTaurus-Littrow Valley. At LPSC, I showed a series of slides discussed the identification of what we called then an ash deposit, a debris flow that comes off of the North Massif, just north of Victory Crater in Taurus-Littrow Valley. The mini-RF monostatic data from early in the LRO mission shows several fissures that essentially cross upslope within the North Massif, including what we called either initially an ancillary fault or indeed a pyroclastic fissure. And that pyroclastic fissure, as it runs down to the base of the North Massif, has this debris flow that is at its foot. We outlined this in a figure in a paper Schmidt et al. Last year. And so basically what we initially identified was there's this debris flow and a secondary ash mantle that extends further out from that debris flow. And we hypothesized in the paper that material from that debris flow would have been sampled at the LRV-7 stop at the southern point of Victory Crater. And so this is another Elrock view. This is a low sun angle, incidence angle of 80 degrees. So if you remember yesterday in my LRO talk, for everyone that was at my LRO talk, I showed a high sun oblique image of the Taurus-Littrow Valley, which really enhanced the color contrast. In this low sun angle nadir view, it enhances the sort of the texture of the surface, and what becomes apparent, especially if you stare at this image for hours and hours, which one can do without noticing time fly by because there's such a rich tapestry of information in this image, that there is this, and the pointer, the remote pointer doesn't seem to be working, but there is this texture difference that we see on the ash deposit. Let me go to the next step, which highlights where we see the main outline of the ash deposit and then the potential extension of that debris flow out south of that feature. To the west, we have the Lee Lincoln scarp terrain that has been identified as this shaken, not stirred terrain, which may have been disrupted by seismic activity, and then the sort of heavily cratered or the cratered floor of the Taurus-Littrow Valley. Notice also where Station 4, another LRV sample, and Camelot Crater are in this image. And so this is another, because you can never have too many Elrock oblique images in a talk. This is a separate view from what I showed yesterday. And I'm going to step to the slide. So for those following online, pardon me for a second. You've got Camelot Crater here, Shorty Crater, I'm sorry, at Station 4, the light mantle finger, and then our ash deposit is featured over here. Victory Crater is located right here. So we've got LRV sample 7, 8, and then Camelot Crater here at Station 5. And so what this image also sort of begins to highlight is that there's indeed a textural difference. You can see there is a pronounced lack of impact craters on this ash deposit, whether that's because it's younger or indeed the actual properties of the material are more unconsolidated, so we don't have as detailed a crater record on that surface is still unclear. I know that Carolyn van de Bogart is going to tackle crater counting on that feature to see if we can get at least a rough estimate of its age, even though it is quite small. We fold in another data set, and this is the wonderful Moon Mineralogy Mapper data set. In our Apollo 17 paper published last year, we included the figure that's at the right, which is the sort of color composite, the standard Ncube color composite, which really does a wonderful job of highlighting the compositional diversities amongst the mafic mineralogies. At left is a principal component analysis that Dan Moriarty prepared for this presentation, and also highlighting the sort of wide range of compositions along the massifs around the Taurus-Littrow Valley. In both views, we see that there's not just a wide variety of compositions, but indeed that this debris flow here, you easy for me to do, does stand out as being distinct. Now, in the paper from the Icarus paper that we published, we really didn't examine the implications of that compositional variation, where we were really more focused on looking at the compositional variations in the sculptured hills. But we turned our attention to this ash deposit as it became clear that there's something unique coming on here that may or may not be represented in the Apollo sample suite. So here are some wonderful Ncube spectra highlighting the compositional diversity. At top is the sort of the raw extracted spectra from multiple compositions across the valley. The purple line at the top there is our debris flow, our ash deposit, and then other features both on the valley floor of the composition of the basalts as well as across the sculptured hills. When we plot the 1 micron and 2 micron band centers against each other, we see that there are clear trends not only in the Apollo 17 data, but also in standard compositions of basalts. So there's several things that are plotted here. The smaller black and gray dots are pure pyroxene compositions and sort of highlighting the known trends in composition as a variation of pyroxene content. In the orange, yellow, green, and different orange colored plots, we see sort of a known trend of basaltic compositions that are seen across the valley. And then in the purple is our ash deposit. And so what that highlighted and what we initially began to interpret at LPSC was, well, this is telling us that it's not only distinct, but it's a really unique composition compared to the rest of the valley. And a preliminary assessment of this that we presented at LPSC is that because it's very low and close to that pyroxene trend, it could represent a unique basaltic composition and perhaps even a very low titanium basalt, because as you move increased titanium in basalts, it moves away from that pyroxene trend. So this is sort of where we were at LPSC. We showed that this was a really unique composition and really wanted to dig more into what this could represent and if we indeed had identified the source of the VLT basalts. And so started looking into what we know about VLT basalts. And of course, VLT basalts are underrepresented in our sample collection. The initial identification of VLT basalts in 1977 in fragments that were in the deep drill core sampled near the LEM, as well as in fragments sampled across the valley, suggested that, okay, there is some abundance of VLT basalts at Apollo 17. It's not a dominant rock type. In some modeling work that Randy Korotev published in the 90s, he suggested that VLT basalts were on the order of about 8% of the regolith across the Taurus-Littrow Valley. What got me most excited about this is that for years there's been this effort to find sources for VLT basalt at Apollo 17, and had to, as much as I love regolith mixing and the idea that you have exotic materials coming from far away, it was nice to find potentially a local source for this material. And over the decades there have been a number of possible sources for the VLT basalts at Apollo 17, including basalts from Mare Crisium, which we know has VLT basalts based on the Luna 24 samples. There are some other local or relatively closer, but still hundreds to thousands of kilometers away sources that had been identified with surface exposures of VLT basalts. So that's where we were as of a couple weeks ago, and thinking, okay, well, maybe we really have identified a VLT basalt source. But something that really lingered was, well, let's compare it to what we have. We actually have these samples. It's remarkable to think that we have the samples, so let's actually look at them. How great is that? I know that Faith Filas is here, and she's worked hard at getting the Luna samples essentially rediscovered in our analysis capability. And so that got us thinking about, well, what we can do in looking at what we actually have on the ground. So let's compare for a moment of what we had at Apollo 17 to Luna 24, and in work that's been done and presented both in the source book and in the New Views of the Moon 1 chapter led by Chip Shearer, is a comparison of what we see at Apollo 17 and Luna 24. We know that the Luna 24 samples had been measured in the relab in Carly's spectral library, and so we thought, well, let's see how good of an analogy that these Luna 24 samples provide in comparison to what we see at Apollo 17. The reason we wanted to do this is because the Apollo 17 fragments are in limited quantities and had not been measured as far as we could tell and are available in the relab. So we wanted to have nice, good laboratory spectra of a VLT basalt. So let's look at Luna 24. First of all, just to refresh everyone's memory, because I'm sure the history of Luna 24 is on top of everyone's mind. Luna 24 returned 170 grams in the third of the robotic sample return missions by the Soviet Union. This was drilled in sort of at an angle, going down to about 200 centimeters below the surface. In preliminary spectral plots that were presented in the Crisium book in the late 70s, John Adams showed that there were a number of spectral characteristics in those plots. And so actually where we started was digitizing those plots because they existed. But as Carly pointed out in her presentation, a lot of this was done by hand. And so the spectra were, while beautiful, not really meaningful in an evaluative sense. So we ended up having to dig into the Relab database. I do want to point out something that Vanneman and Papike reported in talking about these VLT basalts from 17 that's really important. With these soil samples, you get a great representation of compositional diversity. And so without the deep cores and the myriad of soil samples collected by 17 really wouldn't give us a sense of the compositional variation that we now know exists surrounding the landing site. So Dan started by looking at Mare Crisium through Ncube and the WAC titanium estimate to find areas that are possible surface exposures of VLT basalts and comparing them to what we see in Ncube data. So this plot at the right is familiar now. We've seen several versions of this. We've now added, though, a couple different VLT basalt spectra. There's the red X's and the sort of the red dots that represent VLT basalts from both the Relab database as well as what we see from remote sensing data. And you can see that they don't plot anywhere near our North Massif deposit. They all fall roughly along the basaltic trend. And so this was a surprise, but perhaps not that surprising if you take a step back and think about it, that sample, that ash deposit, not exactly represented in these VLT basalts. So we had to take a step back and reassess our assumptions of what this material actually could be. So if the ash deposit's not source of VLT basalts, then what actually is it? We know that we're assuming that we have some sort of extrusive volcanic material. It's a distinct lithology, and it is unique relative to the other Mare basalts. But of course, when Dan is looking at this, Dan is laser focused on one particular area, and that triggered a memory in him of something that looks familiar to that. And that is a nice segue into what Dan will be talking about tomorrow, and that's, of course, everybody's favorite large Farside Basin, SPA. Dan has done a tremendous amount of work in analyzing the pyroxene compositions, the mafic compositions inside SPA, and he's identified this central, what he's called the South Pole Aitken compositional anomaly, which is outlined in a paper published this year, where we see distinct compositional variation radiating out from the center of SPA towards the feldspathic highland terrain outside of it. So we wanted to then say, well, where does our ash deposit fall relative to SPACA? And so here's a figure from Dan's paper from this year showing the pyroxene trends throughout SPA. We have the non-Mare clinopyroxenes, that's the green dots, that's SPACA materials, basaltic clinopyroxene, and then the magnesium pyroxene materials, which form this pyroxene annulus, interpreted to be parts of the SPA impact melt. I should say that these boundaries are somewhat fluid, and in more detailed work looking at the interior of SPA using the full resolution 100 meter, 150 meter per pixel data from Ncube should show that there's a blending between these locations. And so let's just basically plot the two on top of them. So this is a wonderful sort of marriage of different areas, different data sets, but when we plot the SPA trend on top of our basaltic trends, we see, and I'll point out here, our ash deposit plots right at the boundary of the SPACA terrain and the MG annulus in SPA. So that's suggesting that maybe we don't have a low titanium, certainly doesn't appear to be a low titanium basaltic terrain, but we've got something unique. We assume it's volcanic, it's eruptive, and it's unique. So that puts us at this sort of boundary. Well, we know that there's something interesting going on here, but again, we've got samples. Let's not forget, we have samples. So let's dig into the literature for a moment and see what we have. As I mentioned before, we've got samples from the south apex of Victory Crater, LRV7. We've got LRV8 and Station 5 further east. And one of the joys of being able to pick Jack's brain is that there's this wonderful archive of knowledge about everything. And so really just the other day he said, well, what do the soils at Station 5 tell us? Well, then you turn to the mind of Randy Korotev, which is a mysterious, wonderful place. And of course, buried in Randy's 1992 tome on Apollo 17 is this identification of a unique magnesium-rich component in the Station 5 regolith soils. Now, there's a lot of work that has to go on to sort of confirm what we're seeing here, but I'd like to hypothesize that what we're seeing on the North Massif is the source of this high magnesium component. Now, Randy doesn't talk about in the paper whether or not there are similar samples at the LRV stops. Certainly something worth digging into. Indeed, actually as early as 1974, in a look at the Station 5 regolith soil samples, it was also identified that there is this unusual lithology. So I'd like to retract what I said at LPSC in terms of VLT basalts, but protract, outtract, that we maybe have a different component of the regolith here, very unique lithology that has not been found in other locations. Certainly something worth digging into. We also know that those Station 7 soils are very low in olivine, as many of the other soils in this vicinity are. Okay, so where are we at now? So if this is indeed a similar SPACA composition, is there something we can learn about SPACA by analyzing these samples, what they're telling us about the eruptive history? We know that it's perhaps a late stage. This is clearly a mantling unit. So really getting a handle of how young or how old, depending on how you look at it, this deposit is, we may be able to glean some insights into what's been happening inside SPA. And I'd like to just conclude with this sort of thought, and this really resonated, is that we have these samples. This is another mission to the Apollo collection. And by digging into these, not just the pristine samples or the unopened samples, but even what we have, there's still a lot left to learn about the places that we've been and one day hope to go back to. And with that, I'll conclude. Thank you. And now that I have Jim's time, I'd like to go into my next set of slides. No, I'm kidding.
Yeah, the next talk is not happening. It's a technical difficulty.
Yeah, very unfortunately, Jim doesn't have internet access, but I do encourage everyone to read his wonderful one-page abstract on a theoretical model for the formation of ring-mode dome structures. So that brings us to
Discussion
session. And I guess we'll start, since Noah was refusing to make eye contact with the chairs, so we couldn't. Does anyone
I know
have,
that you're just staring lasers at me anyway. So.
Does anyone have any questions for Noah? And then we can open it up to the rest of the 7 talks we had.
I know you've got a question, Carly.
I have to go back and read Randy's paper now.
Yeah. Set aside a few weeks of your time. And
Well, okay.
there we go.
And Dan here too, yeah, good. Because you mentioned that perhaps this unusual composition is associated with SPACA, but in the pyroxene, it was more towards the magnesium end.
Mm-hmm.
So why do you think it's SPACA like?
Well, again, we have to be careful about the boundaries, and I mean, Dan can answer this. Just nod if I get too far off track. But those boundaries, let's not call those aren't hard and fast. And it's going to require a little bit more, again, of that full resolution analysis to see where that boundary actually exists. And maybe, maybe it has nothing to do, well, I would suspect there's some relationship there. And again, I'm not saying that what we see at Apollo 17 is from SPA. This is not SPA ejecta coming. This is, but there may be a process that's occurring there that we have to think
sort of
about.
Implying it's basalt. Could it not be part of the magnesium suite?
Absolutely.
Oh, okay.
Yeah. Yeah. I mean, I'm implying that we have to think about it more.
Okay. Yeah. Nevertheless, it's cool.
Yeah.
Yeah, so I think kind of the starting point for that hypothesis is that texturally and geomorphologically this looks volcanic.
Mm-hmm.
None of the kind of basaltic materials we looked at had a similar composition at all. So when we plotted it against SPACA, it was close enough to the neighborhood where that's one possibility for this kind of more magnesian volcanic material. I would say at this point it's not inconsistent rather than it's consistent, if that makes sense.
Maybe flip it around, and this will be tomorrow's discussion. Maybe SPACA is a low titanium basalt. Very low titanium basalt, excuse me.
The VLTs we have looked at do look more kind of typically basaltic in the pyroxene compositions, where SPACA is more of an intermediate pyroxene composition between the magnesium and the kind of basaltic.
I'd just add that the The two LRV samples are unique for that particular area. The LRV4 at Victory Crater has about 16% volcanic ash in it. And it suggested to me that you had and also a low median particle size. And it suggested to me at the time that you had a plume of volatiles and ash coming off that debris flow as it came to a stop. And that's what we sampled at Victory Crater. And I even made a comment driving by that everything looked like it was mantled. That's in the transcript. And then I noticed that with the sample 75121 at the LRV stop 8, that it had very low ilmenite, even though it's out on the dark mantle, which is basically generally an ilmenite-rich regolith. The ilmenite content, at least in the Heiken and McKay analysis, is less than 1%. And it also has a low median particle size. And that suggests to me that it might be part of that same plume, except it's the Massif material that has been remobilized in the plume off to the edge of that debris flow. So there's a number of things that are reasonably consistent with that being a debris flow and with us maybe even having samples that came off of it.
Really what I'd like to do, well, I'd like to get a beer right now, but what I'd really like to do is get some of that fraction that Randy identified into a high quality. Sarah?
I'll find out.
There you go. Boom.
Any more?
Can we stop the Inquisition and open it to everyone else?
Yeah, sure. So let's see. So just to recap, so we had Ian, Megan, Carly, Licia talk